Hello and welcome to this series of videos which is going to be called elementary geometry, and my point of these videos is to get you through some very simple geometry theorems and get you started on serious geometry as soon as possible, possibly to give you a good start. So in this series, the first theorem I've picked up is one of my all-time favorite theorems in starting geometry, and I shall now proceed to tell you what the theorem is. So I shall also give you a justification of why this is my favorite theorem from elementary geometry. So the theorem goes like this. It says that you pick up any line segment AB and you drop a perpendicular bisector onto this line, and let's say this is perpendicular bisector in the sense that these two pieces are the same length. Then you pick up any point P on the perpendicular bisector, and the theorem says that your distance from A will be equal to your distance from P. You are at P, so let's call this distance C. So C will be the same on both sides is to be proved. So this is one part of the theorem, and the converse is also true. Together this forms my favorite theorem from very elementary geometry. Converse is also true. So the converse says that if there's the line segment and you happen to find yourself in a place and you find out that you happen to be equidistant from both the endpoints of the segment A and B, and so these lengths happen to be same, you can be sure that you happen to be residing on the perpendicular bisector of this segment AB. In other words, the perpendicular bisector, that is the red line, perpendicular bisector, that is the red line, will pass through something that is perpendicular as well as something that bisects the line, will pass through your location, which is P. So let's prove both the theorems and then try to justify why I rate it very highly. Okay, the reason I rate it very highly is that it quickly leads to two very pretty results. Let's talk about it for later. Let's just finish the proof now. The proof will use Pythagoras theorem. Now that itself is a fun thing in geometry, to prove Pythagoras theorem. Maybe we'll save it for some other day. So let's prove the first part of the theorem, which says that if you actually drop a perpendicular bisector and you take any point on the perpendicular bisector, let's say P, then you will find that the distance from A and B will be equal. It's fairly simple proof, follows directly from the Pythagoras theorem. So the first thing you notice is that since it's a bisector, the length, let's call it D then, length AD and DB are equal, and let's call this something, it doesn't matter what you call it, let's call this Y, and what one realizes is AP is equal to square root of x square plus y square, but BP is also square root of x square plus y square. I'm using the Pythagoras theorem, and before I forget, the reason I'm allowed to use Pythagoras theorem is because it's a perpendicular bisector and this is 90 degrees. Right. The proof of the converse proceeds along similar lines. You are given that you happen to find yourself at a point P, and you happen to find yourself equidistant from A and B. Now you have to show that the perpendicular that you draw from P, well, you can definitely draw a perpendicular from P onto the line segment, so this is 90, and what you have to show is that this perpendicular happens to be the perpendicular bisector. In other words, you have to show that these two lengths are equal. That means you have to show that AD equals to DB. So is this equal? Well, pretty much the same. AD is equal to root of, let's again call this length as y. Now AD is equal to root of c square minus y square. Once again I'm using the Pythagoras theorem. And pretty much the same thing, BD is equal to square root of c square minus y square. Please refer to the figure. All I'm doing is using the Pythagoras theorem. Okay, so that's the end of the proof. A very simple proof. Rests on another great theorem on the shoulders of the Pythagoras theorem. Well, now let me proceed to show you why I rate it so highly. Two very pretty results, and which I mean, there are many, but these two are used a lot in elementary geometry. So I pick up a parallelogram, a specific parallelogram whose four sides are equal, and such a parallelogram is called a rhombus. And one nice property of the rhombus is that if you take the diagonals, then the diagonals bisect each other, and very nice fact is that they are perpendicular. So the diagonals of a rhombus are perpendicular to each other, perpendicular bisectors of each other. So this point also happens to be the midpoint of both the diagonals. Okay, so this can be proved in just two lines, I think, thanks to our favorite theorem. So the way it goes is A is equidistant from B and D. That's the first statement. The second thing is C is also equidistant. I think I won't write this, from B and D, and this implies from our previous theorem that AC is the perpendicular bisector of BD, and using the same reasoning, BD is the perpendicular bisector of AC, and that ends the proof. So such a two-line proof for a very nice fact about the rhombus. The next one is one of my all-time favorites, and that goes like this. Take any triangle. Now I am just drawing some arbitrary triangle. Take the triangle and let's call it ABC, sorry, and let's follow the construction where I draw a perpendicular bisector. Remember that the theme of the whole video is the perpendicular bisector, so better perpendicular bisector. So let's just make sure that we highlight what we're talking about. Okay, so let's proceed to draw the perpendicular bisector of one of the sides. So it goes like this. So it is a perpendicular and it's a bisector. Let's do the same thing for another side. So maybe like this. Okay, so once again this is a perpendicular bisector, this time of side AC, this time of side AC. Now these two perpendiculars bisect at a very special point, and we shall call it C. Okay, this C has a very interesting property which we shall now write down. So just to make sure that I don't lose you, I'm actually going to write it down. The two key statements that follows from this construction. The first is that C is equidistant from A and B, and the reason is that it lies on perpendicular bisector of AB. So let's put it down, whatever we've just written down on the figure. We are saying that this distance and this distance are equal. So let's also give it some name. Now I shall call it R, and you'll realize why in a minute. Okay, but there is still something more special about C, and that's the second part of the proof. C is equidistant from A and C, and the reason is it lies on the perpendicular bisector of AC. So that means that I should try to put this down. The distance of C from, okay, so there is some problem here. This is also C, so let's just call it C dash. Okay, C dash is equidistant from C and A. And how do I mark this? I can say that this length and this length is same, but that length we have already given it the name R, so this shall also be R. And here it is, C dash is really special. Okay, if I put my sharp end of the compass at C dash and measure out the length R, measure out this length R and draw an arc, okay, it won't be surprising that it passes through all the C3 points. So this circle actually will turn out to be the circumscribed circle of the triangle. This is a very beautiful simple construction, but all I want to highlight is the fact that the proof follows from what I call my favorite theorem in elementary